So you want to learn about fluid mechanics. That's awesome. Yeah, that's better. So what we're trying to do here is to have a nice course in fluid mechanics that strikes to have a balance between just being general interest, but really also gives you qualifications as an engineer. So I try to make it more interesting. We'll see how that works out. But at the same time, what is really important to realize is that it takes a lot of work on your part. This is a topic that you can't just read about or watch a video about. You really, at some point, have to sit down, take pen and pencil, and solve actual problems, go through actual equations. Fluid mechanics is super exciting. It's everywhere around us. We have that in our everyday lives, when we pour coffee, when we water our garden, when we take a shower. We have it in technology, aircraft flying, whether it's car aerodynamics. It could be injection of fuel into cars. It could be combustion. It could be weather, clouds. It really is everywhere. I personally find it's at a super exciting intersection between math on one side, really the mechanical aspect of it. You sometimes go into computing, and that's just incidentally what I do, and just really the fundamental physics of it. But a good companion there is necessarily a book. So let's talk about books. If you learn with an instructor, the instructor will tell you exactly which books he or she will like. This is one that I just happen to use. And I think the key thing here really is that fundamentals of fluid mechanics isn't a topic where a lot has changed in the last 100 years. Nowadays, the big differences are things like that. I'm not endorsing anything here. It's just that there's a lot of supplemental material available that could make your life or the life of the instructor easier, such as videos or exams. Topic really hasn't changed all that much. This here, for example, may be one of the oldest fluid mechanics textbooks, maybe the original fluid mechanics textbooks by Prantl and Tietjen. And while this certainly is a lot nicer book, like if you're buying one of these new, it could be anywhere beyond $100. I got this one here for $10 used on Amazon. And let me just show you that really they're very, very similar down to illustrations. Pressure prism. Static pressure in vessels of different shapes. Buoyancy and stability of boats. So you've picked your book and you're serious about learning fluid mechanics. So that's excellent. But now really the question is, how do you go about it? This is a difficult topic. And I think 3 steps are really crucial to master fluid mechanics. The first one is to pick a book. Any really, ideally the one your instructor is using, because it'll make it easier for you to refer to certain equations or examples. But take that book and read the chapters. Part 2 is really that it's not enough to just read the chapters. But instead what you have to do is, as I said, this is very math heavy. And you could say fluid mechanics started becoming a science only when engineers started doing math and really using that. So what you will need to do is to read your chapters, but not just read equations, but you have to go through your equations step by step and be able to understand every single step. And really, once you've done that, close your book and be able to reproduce the derivation without looking into the book. Only then do you know that you've actually understood it. because it's so simple to just read through something and say, oh yeah, that makes sense. It's not yet there in your brain. You have to make it yourself. And the third is, do examples. Many examples. As many as can get hold on. You got the whole internet for you. You can look at exams that were published. You can look at Shams outline. You can look at certain examples other people used to explain something. Go through them. Work your way through them just as you're reading a book. Follow each and every single step and then recreate that without looking into the book. And what you want to see is a trajectory from when you start out and you apply the same law, the same principle to different situations. It will look like, oh, this is a completely different science for every different application. Like, how will I ever be able to solve this for things I haven't seen before? But as you go along, you'll see the patterns. And once those patterns have become obvious to you, you will think, oh, this is always the same stuff. And that's where you want to be. Once you realize that it's always the same, that means you've mastered that particular topic. Finally, I think it's really simple to trick yourself into thinking that you are learning when you're not. It's not enough to just read the book. It's not enough to just go over the equations and say, I understood them. It's not enough to just watch a video and say, oh, that makes sense, whatever that person is saying. So it's not enough to just say, I understand, but really the crucial step is for you to be able to recreate what you learned. When you're watching videos, when you're just skimming through the book, it may feel like learning, but you're actually not. It really, at some point, you have to sit down, you have to take pen and paper, and you have to go through those equations step by step and solve those problems yourself. Otherwise, you won't understand. So, why did I actually have you watch through that wannabe cinematic scene with me making coffee? You may have noticed that there's really already a lot of fluid mechanics involved. So turn on the faucet, really. And then water comes out and collects in the mug that I'm using. So the question here arises, what makes that water move? And we'll talk about that. And really what we have in the end is essentially a reservoir here with a certain pressure. And we will understand how that pressure translates into movement of fluid and thus into mass flow rate or velocity of the water stream leaving that faucet. So then I took that and placed all that in the coffee machine. So I fill that up to the top. So questions naturally arising now are, well, what is actually the pressure down here? Pressing against those walls. What is the pressure of the water that wants to leave here? And what happens to the water? So a coffee machine has a heating element down there. Our water will go through here. And then what happens is that the supplied energy is enough to overcome intermolecular forces. So our water molecules, well, the molecules stay together, but the individual molecules separate from each other. So we have vaporized water rising and ultimately collecting in the top part, where it condenses again, releasing heat. So that we have then liquid hot water streaming further. So we now here have our filter with coffee powder. And below that, again, the vessel with which we will want to collect the water. So the water makes its way here through the ground coffee and collects the molecules that are responsible for the taste of coffee, and then drips out at the bottom so that here, in the end, coffee forms. So we already have a plethora of physical phenomena going on here, right? We have here at the top, we have pressure driving a certain flow so that we have the water finally collecting in our little kettle. We have then in the coffee machine this phenomenon where we have pressure, it's stored, the fluid wants to get out, it is then heated and vaporized. We have a phase transition, we have more phase transition. Once it has moved up here, we have heat transfer here. We then have some complex multi-phase porous flow here where our water collects certain molecules, absorbs them, and until it's finally here in coffee, which itself is a complex mixture and very much different from the initial product that we used. Now, this is only an introductory course, so we'll not talk about many of these phenomena. We will not talk about phase transitions. We will not talk about heat transfer. We will not talk about absorption processes. We will not talk about multi-phase mixtures. But trust me when I tell you that everything that happens on this side of the drawing is already pretty complex. I'll give you another example, and that is maybe a bit closer really to what we'll do. This is an experiment that I hope many of you have done. That is, we take a bottle, we put some water in it, we don't fill it all that, and then we attach an air pump here. And when we pressurize it, what happens is that air bubbles rise up and ultimately collect up here and make the pressure P go up. So when we disconnect the valve, what happens then is that the water is pushed out by the overpressure in the reservoir. So we have a reservoir here. We have water here. And again, this is a simple water bottle rocket. So this simple system already has a lot of interesting questions for us. For example, what is the pressure that we need to supply down here that can actually make its way against the water pressure? What happens when the water comes out? What is the force or the thrust that this water jet has? And then following Newton, what is the acceleration of the rocket as it's taking off? We can look more closely into what is going on here. So we have a flow of water through a pipe, essentially. And what we learn is that water, or any fluid really, will stick to the walls and will be fastest in the center, far away. So that is very much similar to what you experience maybe in a mall or something. When you go through the hallways, people will look through the windows and they're put there, and in the middle, people are just faster. So a fluid does the same thing. Now we have a complex velocity distribution here. And how does that affect the forces when that is ejected? Also, is the flow that comes out there always orderly or laminar, or is it maybe turbulent or more volatile? We will look at the flow surrounding an object like that. So as we have an object like that moving through the air, it will push away the air. It will make its way through the air. So that is, we have air coming in here. It'll stop right on the surface. Here it needs to go past it. It'll accelerate. But we'll ask the question, can we actually calculate a velocity field around a body like that as it changes as our body moves? And then how is the velocity field related to a pressure field, and how is all of that related to forces acting on that body? So with that, I'd like to conclude for this very first video here. I think I've given you a little bit of introduction about how I think we'll do the course, what I think is essential for you to learn fluid mechanics, and we'll continue with more specific examples then in the next video.